All right, so we are going to be doing decoding color codes for 4-band resistors or resistor. So let me give you a hypothetical combination of colors. Let's say I start off with a VIO dash RED dash YEL dash SIL. And given these in this order, I would be looking for several things. Coded value. I would be looking for a maximum. And I would be looking for a minimum. All right, so we have a VIO, RED, YEL, SIL. So everybody, you should have this information in your journals, yeah? In your journals, you are only allowed 2 things to go in there. One is my card and one is the magic card. So that being said, you should have that handy in your journals. So you pull that out, and each color band in its position has a very specific meaning. All right, so what are those meanings? So we have first band, you have a second band, you have a third band, and you have a fourth band. All right, so if we could, Rodrigo, what is the meaning of the first band? What does the first band represent to us?
The first digit.
First digit of the value. Everybody remember? So first digit of value. And then what does the second band represent for us? Robert? This represents, yes, second digit of the value. Okay, very good. Second digit of the value. What does the third band represent for us, Brad?
Multiplier and the number of zeros.
Okay, so it could be called multiplier or number of zeros. That's what the third band represents for us. What does the fourth band represent for us, Sarah?
Tolerance.
Tolerance. T-O-L-E-R-A-N-C-E, tolerance. And the meaning of the word tolerance, Wei Ji? How would you describe tolerance to the middle school cousin that just walked in for resistors? It means what to us?
Difference to want to make to the system.
Yes, it would be the difference. I would rather have you think about these words, okay? It could be percent of error, okay? Think about it as a percent of error, because from the manufacturer, they want to be as consistent as possible, but sometimes as they mix the chemistry together, they're not able to get exactly the value that they code. All right, so this is an interpretation of how to read a 4-band resistor. First band is first digit. Second band is second digit. Third band is third digit, not third digit, but multiplier or number of zeros. Fourth band is tolerance, which means percent of error. So now let's go ahead and decode this guy. So the first band being violet, Isaac, what is the value of my first band?
It's going to be 7.
A 7. How many people agree it's going to be a 7? So you write down a 7. That's your first digit. Very good. The second band tells us a second value. Yusuf, what is my second value?
2.
It's going to be a 2. How many people agree that that should be a 2? So far, so good? All right. Our third band, Jacqueline, is multiplier or number of zeros. So what am I going to do here? How many people agree we should tag 4 zeros behind the first 2 digits? Everybody good with that? So 1, 2, 3, 4 zeros. And then what do this is my worksheet. This is my answers go up here, but my worksheet is here. So what else do I need to write down on my worksheet? Question goes to Dimitros. What do I write down right here? Our percentage of error. Before we do that, we do have a symbol for resistance. The unit of resistance class is what? Ohms, and the symbol for ohms is what? The omega symbol. So we write down the omega symbol, this horseshoe-shaped thing, because this is, if you look at this, isn't this 720,000 ohms? Okay. Now we will do the percent of error. So plus minus some percent of error. So Dimitros, I happen to have silver. So what is my percent of error for silver? See that on your card?
Look at tolerance.
Look at tolerance. Okay, so it would be plus or minus 10% is how we should speak it, okay? So Dimitros, try that again. Okay, so we already have the plus minus on the paper. Now we put down 10%. So this is our worksheet. Now we're going to transfer this information to the answer sheet, the answer blank. Now we don't have space to do 720,000. We're going to have to translate this into proper engineering notation. How do I do this in proper engineering notation? Well, you have a calculator. So turn on your calculator and enter 720,000, 720 followed by 3 more zeros. Does my calculator show 720,000? Does your calculator show 720,000? Go ahead and hit the equal button. When you hit equals, what does it show you? It shows you scientific notation, which is 1 digit, 1 decimal point, followed by some digits. What's my power of 10? That's useless to us, right? We need this in engineering notation, which, how do we know it's not engineering notation? The exponent is not a multiple of what? It's not a multiple of 3. This is 10 exponent of 5. So how do I get my calculator to translate this into proper engineering notation? Do I have an ENG key here, the engineering key? And if I go to tap this guy, the decimal point will automatically move and the power of 10 will automatically change. So watch my display. Right now it's in scientific notation. I'm going to tap the engineering key and in a moment, voila. Does my calculator go automatically into engineering mode and give me the correct engineering? Yes.
Can you do the first step of it again?
First step of what?
The calculator part?
Yes, I will clear the calculator. So now the calculator is clear, yeah? I will enter into the calculator the value that we wrote down on paper, 72 followed by 4 zeros. So 72 followed by 4 zeros. So now does the value on my calculator match what it is that we have written down on paper? So far, so good? Then I will hit the equal key. The equal key will put this into some form of exponents. When we look at it, the very first thing that it gives us is what we call scientific notation, which I said was useless to us because it's a single digit, single decimal point, digits, and some power of 10. And this power of 10 is not a multiple of 3. This power of 10 is 5. So I have to shift this into some power of 3. The way that I do this is I hit my engineering key. So if I touch my engineering key, watch the display change. Did the display change to show us some power that is a multiple of 3? It could be, well, it could be 10 power of 6, 10 power of 9, 10 power of 12, or 10 power negative 3, 10 power negative 6, 10 power negative 9, but it has to be some multiple of 3. And right now it happens to be 10 power 3. And what's my value in front of the decimal point? 720. So what am I going to write down on my answer sheet? On my answer sheet, the question goes to Rodrigo. What am I going to write down? Based on what my calculator shows, what am I going to write down?
720 kilos.
So 720, correct. And you look up on your magic card, your 10 power 3, your magic card should show you kilo, yes? Is that right? For 10 power positive 3? This is not negative 3, it's positive 3, because there's no negative symbol in front of this exponent here. So that represents kilo. So you write down the lowercase k, and you write down omega. Is everybody okay with how to express the answer in proper engineering notation? So far, so good? All right, now we're going to multiply by our decimal multipliers to very quickly get minimum and maximum. To get maximum means what? Take a look at my percentage error. My percentage error is plus 10%. What is 100%? What is 100%? Add 10%. What is 100% plus 10%? 110%, yes? 110% means we've added the 10% back in. So what is 110% as a decimal? 1.1. This is what you're going to use to multiply this value by. While this value is still on the display of your calculator, trying to hold this so I can catch the light. So everybody sees 720 kilo on my calculator. Don't clear it because it's right there. All you have to do is take this number on your calculator and multiply by 1.1. So now times, watch what happened when I hit the times key. When I hit the times key, what came up on the far left-hand side of the calculator? Answer, meaning the previous answer, which was the 720 kilo. Now it's going to multiply by whatever I key. So I'm going to key in 1.1. So by doing this, it takes the previous calculation times 1.1. And if I hit enter now, I end up with some goofy scientific notation, which we know is useless to us. So what do? Hit the engineering key. And are you doing this on your calculators? This is not watch and enjoy. This is you do and practice. Don't practice at home, practice now. Because if you don't know how to use your calculator, I can help you now. So what do we see? Your display of the calculator should show you this. What answer do I write down on paper, Weiji?
792 kilo ohms.
792 kilo ohms. Everybody okay with how we determine that and what I write down on paper? Everybody good with that so far? Cool. Now, one more to do for minimum. And minimum would be subtract 10%. Yes, remember it's plus or minus 10%. So let's go ahead and see if we can determine that. So we will have, what is 100%? And I'm going to take away 10%. What's that leave us with?
90%.
90%. What is 90% as a decimal? 0.9, or just simply 0.9. So could I take the coded value of 720K and multiply by 0.9 as my multiplier now for tolerance? So watch this. I'm going to clear my calculator. Is your calculator clear? My calculator is clear. What you're going to do is you're going to key in 720 kilo. And here's where a lot of people, for first semester students, they miss this. They just simply key in 720 and multiply by 0.9. Now, we'd be wrong. This is 720 kilo. So watch how we have to do this on our calculators. 720. How do I key in the value of kilo into my calculator? I have an EXP button right here. Here's my EXP button. When I touch the EXP button, it automatically creates a times 10 function. So EXP on this calculator is the same function as second double E on our TI-84s. It's the same function as this key. On some calculators, it's shown as times 10 to the X power. All three sets mean the same thing. But on our calculator, since we happen to have EXP, I press EXP and it shows E in the on the display. And kilo is what power of 10? 3. So I simply enter 3. So now does my calculator display show 720 kilo? Is that a positive 3 or should that be a negative 3?
Positive.
Yeah, because kilo is a positive 3. So now can I multiply this by my decimal 0.9 over here?
Yes.
So times 0.9, and I end up again with some scientific notation. What do? Hit the engineering key. And when I hit the engineering key, it automatically shifts. And so the value we write down on our answer sheet should be what value, Isaac?
What was the question?
The question is, what value do I write down for minimum? It's on the display of my calculator.
648 kilo ohms.
Excellent. 648 kilo, because that's my 10 power 3, and write down the omega. There we go. So is everybody happy with how to decode a 4-band resistor? This is good review. We've done this once before, a couple times before, and this is good practice for us for the process. Everybody good with this so far?
Yes.
All right, so the next thing we're going to do is to decode a 5-band resistor. So decoding 5-band resistor. And the 5 color bands that I'm going to give you in this sequence will be as follows. GRY dash ORN dash WHT dash GRN dash RED. And again, I am looking for coded. I am looking for max, and I am looking for minimum. So those are the 3 things that we're looking for. So as before, my first band represents something. My second band represents something. My third band represents something. My fourth band represents something. And my fifth band represents something also. So what does the first band represent for us, Yusuf? We'll call on you again. What is my, no, what does it represent? No numerals, but conceptually, what's it represent?
It represents the first digit.
Excellent. So it represents the first digit. And what is the value of the first digit in this case, sir?
8.
How many people agree that the first digit should be an 8? 8. Second band, thank you, sir. Second band, Jacqueline? Second band represents what?
Second band represents second digit.
Second digit, good. And what is the value of the second digit in this case?
3.
How many people agree it should be 3? Okay, I have 3. Nice. And the third band, Demetros, what does the third band represent for us? No. Before the number, yes, it is going to be a 9. You're correct. But what does it? Third digit, yes. In this case, it is the third digit. Thank you. And the fourth band represents what information, Rodrigo? Is this a fourth digit?
Multiplier.
No, yeah, it's the multiplier. It could be multiplier or what?
Number of zeros.
Number of zeros. Very good. And so GRN says, how many zeros are we going to add to this?
5.
1, 2, 3, 4, 5 zeros. Okay. And what do I follow this up with, Robert? What do I write after the sequence of zeros? This is a resistor, which is measured in units of ohms. And what's the symbol for ohms? Omega. So I have to write an omega symbol here, right, everybody? I need that, absolutely essential. Then I'm on my fifth band. Thank you, Robert. Brad, what's my fifth band represent to us? Tolerance. What's another explanation for tolerance?
Percentage of error.
Percent error. Okay. And what is my percent error in this case?
It is 2%,
I should speak this as what, 2%?
2%,
I should speak this as plus or minus 2%. Everybody? It should be plus or minus, meaning it can go up by 2% or it can go down by 2%. That's how we should speak it. Okay, is everybody okay with the coded value with our practice in writing things out so far? Now, just to help us out, let's go ahead and mark our commas every 3 decimal places. So here is decimal point. So count 3 places, mark a comma. Count another 3 spaces, mark a comma. So how would you speak this value? How would you speak this value in English terms if this were the US budget? Sarah.
83.9 million ohms.
Okay, so 83.9 million ohms. How many people agree it would be 83.9 million ohms? So far, so good? All right. So that's how we would speak it in English. How do I write down the coded value based on 83.9 million ohms? Million. What power of 10 is a million? Look at your magic card. 10 power of 6. So 10 power of 6, is that associated with some metric prefix?
Mega.
Mega. Does mega have a symbol? Is that a lowercase m or a capital M?
Capital.
Is there a difference between lowercase m and capital M?
Yes.
You betcha. Would you like your paycheck in lowercase m dollars or capital M dollars?
Capital M.
Yeah, right? You don't want to be paid in fractions of a penny. I beg your pardon, right? Okay, so I am looking for the coded value and proper engineering notation. Question goes to Isaac.
29, capital M.
No, it wouldn't be 800, my friend. So here's what we did earlier that might help you out. Turn on your calculator. Can we key this information directly into the calculator?
Oh, it would be 83.9 M ohms.
Okay,
Let's say.
so yes, it would be 83.9. Is that lowercase m or capital M, my friend? I didn't hear that.
Capital M.
Capital M with the omega symbol. And how do I speak or pronounce the capital M?
Mega.
Mega. So is everybody in agreement? What we have here is 83.9 mega ohms. And if you're not sure about this, you can always key this into the calculator, yeah? You can always key in exactly what you interpreted over here on paper. And so it would be 83 followed by 839 followed by 5 zeros. 1, 2, 3, 4, 5. Are you watching me do this or are you doing this? Everybody should practice, right? 839 followed by 5 zeros. And then hit equals. What's my power of 10 on the display of my calculator? 7, which is useless to us, right? Because it's not a multiple of 3. So how do I fix this? Hit the engineering button, and voila. Does the engineering button show you exactly what Isaac called us out to read? 83.9 with a 10 power of 6, which we interpret properly as 83.9 capital M for mega ohms. Is everybody okay with the coded value as it stands? All right. Now we're going to do maximum and minimum. So what is 100%? And we're going to add 2%. So what is 100% plus 2%, Youssef?
102%.
102%. What is 102% as a decimal, my friend?
1.02.
1.02. Does everybody understand what we're going to need to multiply by in order to calculate maximum?
Yeah.
Okay, so while this number is on the display of the calculator, still there, multiply that by 1.02. Enter. Engineering. And what value are we going to write down for maximum? Question goes to Mr. Benavides. Robert.
85.58.
85.58.
58.
Should it be 5.7 or 5.8, class?
Okay.
What's it say on your calculator? It says 578, you're right. And you look at the third digit, which tells you how to round the second digit. It becomes 0.58 as your classmate described correctly. So here's the display of the calculator. Yeah, and we would write down mega ohms. So if you look at the calculator, it's 85.578. That third digit tells you how to round the second digit after the decimal point. Remember, we said 5 and up, round up, and this is greater than 5, so we round up the 0.57 to become 0.58.
For max, it's, we're adding the,
Yeah, for maximum, you're adding the 2%.
Oh.
Yeah, for minimum, we will be taking away the 2%. Okay? So is everybody okay with the maximum coded as 85.58% mega ohms?
Yes.
Good. So now, one more thing to do. How about the minimum? The minimum would be 100% minus the 2%. What's 100% minus 2%, class? 98%. And what's 98% as a decimal, class? 0.98. So that's how you can very quickly multiply our original coded value to get the minimum. So here, I will clear my calculator and go through the steps with you. Calculator is cleared. I'm going to enter the original coded value of 83.9. How do I key in mega? I can't forget this. A lot of students forget this. They just put in 83.9 times 0.98 wrong. So how do I key in mega? I have to remember mega is what power of 10? So I hit exponent right here. And then I hit 6. And now the display of my calculator should nicely show 83.9 mega. Now I'm going to multiply this by my decimal 0.98 from over here. So times 0.98 and hit enter. Scientific notation does us no good. So I'm going to hit engineering. And when I hit engineering, I get more than 2 digits after the decimal point. What value am I going to write down on paper? Question goes to Sarah. You're up. What do I write down for my minimum based on the work that we've done?
82.22 mega ohms.
82.22 mega ohms. Is everybody okay with that? So far, so good? Nice. Any questions on how to decode our 5-band resistor? Good with that?
Yes.
Cool beans. All right. Next task at hand is will be voltages and voltages for a circuit at specific points. So I'm going to draw you this circuit here, 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 like so, to here. And I'm going to put a ground point right here. And this will be R1, this will be R2, this will be R3. This will be 120 ohms. This will be 270 ohms. And this will be, let's see here, let's make this 95 ohms. And for the voltage, I'm going to give us a Vs that is equal to, let's say 12 volts. And I'm going to have the following points. So here's point A, Here is point B. Here is point C. Here is point D. Here is point E. And way over here will be point F. So far, so good? Okay. We're going to set up very quickly a VIR. I'm going to skip the power as it's something we don't have to do right at this moment. For R1, for R2, for R3 totals. The R column is going to be fairly minimal. So here is R. And the rest will be V and I. You want to create these columns wide enough so that you can write your values down that could be microamps or milliamps. You want to be able to have the space to be able to write in your values. So there's your circuit, there's your voltage source, here's your chart for VIR. And let's go ahead and have this up here to remind ourselves Ohm's law, V, I, and R. All right, what would be a good place for us to start filling in this table? We have 3 columns, 4 rows, a total of 12 cells. So we're trying to go for maximum points of all 12 cells filled in. So question goes to Wei Ji.
Yes.
What's the first thing you would do to fill in some values here?
The total voltage and the total and resistance.
Okay, we will go ahead and do our given values, yeah? So our given value is 120 ohms for the first resistor, so 120 ohms goes here. We are also given 270 ohms that will go here. We are given 95 ohms that will go here. And we're given total voltage of 12 volts, which will be in the voltage column, but on the last row. So 12 volts. Is everybody clear on how we begin the exercise? So far, so good? Yay? All right. Now, what would be the very next thing that we would do to start filling in some of the rest of this? Isaac, you're up.
No idea.
Okay. Yusuf, what would be the thing that you would do?
Total resistance?
Total resistance. How many people vote for total resistance? Because you remember in a series circuit, should all the ohms add up to give you a total, right? So you can't do Ohm's law, but you can add the ohms together. So everybody remember that. The very first thing you would do is you need to find total ohms. How do we find total ohms? Add these numbers together. So you whip out the calculator, you hit clear, and you start entering your values for these resistances. So 120, and you add 270, and you add 95. Then you're going to hit equals. And when you hit equals, you end up with some non-scientific, non-engineering value. Hit ENG, and the value you calculate, Jacqueline, would be what?
485 ohms.
How many people agree with 485 ohms? All right. Before you write that down, what should we do?
Recalculate.
Recalculate. Why?
Make sure you're correct.
Make sure this one is, you're really confident with this because everything else depends on this calculation being correct. Okay? So we have 485, let's clear, and let's see if we end up with 485 again. So on our calculator, we're going to key back in 120 plus 270 plus 95 equals, hit engineering. Do we end up with 485 ohms again? Now we're feeling really good. So we will now write down 485 ohms. Do not write it down unless you have calculated it twice. Does that make sense? Is that right cautionary move? Okay, so Jacqueline, what would we do next? We filled in the entire R column. What's next for us to do?
Calculate total amps.
Total amps, total current. Would that be appropriate, everybody? Take a look at Ohm's law. Ohm's law says as long as you have two quantities, you can calculate the third. Well, take a look at the first row. In the first row, do I have, I only have one quantity, so I can't do nothing on the first row. Take a look at the second row. Also, I can do nothing. Take a look at the third row. Nothing for me to calculate. But in the last row, don't I have two quantities right here that will allow me to calculate the current in the middle? And if you look at the Ohm's law formula, what does the formula show you? I is equal to what? But put your finger over the I, like I'm doing. I is equal to what according to my circle?
V over R.
V over R. Do I have a V? Do I have an R? Can I enter this into my calculator? So key in 12 right now. Divide by 485. Hit enter. Again, that's not a good value. It's some power other than multiple of 3. So what do? Hit engineering. And when I hit engineering, the value that we should all agree on, we hope, Demetrios, what do you calculate? I'm looking for 2 digits after the decimal point for our class. So it's 24 point what? Okay, 24.74. And do you see some power of 10 on the far right-hand side of your calculator display? And what do you see? Minus 0.3, yes? Negative 3 power. What does your magic card tell you for 10 power negative 3? Look at your magic card.
No.
We pronounce that as milli. So what is the symbol for milli, Dimitros? You find it there, pal? Yeah, is that a capital M or lowercase m? Lowercase m. So how many people agree? We write a lowercase m, and my electrical units are what for current? Amps. What's my symbol for amps? Capital A. Are these distinctly different size letters? Lowercase m, capital A. 24.74 milliamps. How many people agree with that so far? Okay. Now, before we go on, we should double check this value, yes?
Yes.
Okay, so we clear the calculator. Is your calculator cleared?
Yes.
Do it again, quickly. Now, 12 divide by 485 equals engineering. Do you agree that the answer you recalculated should be written down as 24.74 milliamps? Are we happy with that, everybody?
Yes.
Now that we agree that that is the correct value of current, what would be the next thing we would do here? Rodrigo?
Fill in the rest of the currents with the same, because the series circuit.
Ah, you would be filling in all of these cells with the same value because what do you remember is the same in a series circuit? Current is the same, right? Good job. So you can now fill this in with confidence. 24.74 milliamps right here. 24.74 milliamps. And even though they're supposed to be the same, suppose you didn't double check this very first calculation of current. Suppose this current value was miscalculated and you filled in the entire column. Would that be a problem?
Yes.
Oh, big problem. No bueno. Big time. All right, we got 2 columns filled in. So far, so good? Now, what would we do next, Robert?
Ohm's law.
Ohm's law to find what?
Voltage.
To find voltage. Do we have on the first row 2 values that will allow us to calculate this very first value of VR1? That would be, if I cover up the V in my circle, Robert, V would be equal to what?
I times R.
So V is equal to the I times the R, yes? So I have a value of I and I have a value of R. So let's practice this calculation together. I'm going to clear the calculator. So everybody, how do I key in 24.74 milli on our calculator? Let me move this up so we can see. So you key in 24.74, and milli is exponent of what power of 10? So exponent, so you hit the EXP key. How do I find milli on my calculator? How do I find the -3? Do I have a change sign key that I'm pointing to right now? Look at my calculator, look at my display. Everybody see this negative symbol? Hit negative, hit 3. Does your display look like my display right now? 24.74 exponent -3. And you're going to multiply this by what? By 120. So times 120, and then hit equals, and then hit, no, we don't have to hit engineering in this case. So what value would we write down, Robert?
2.97, 2.97 milli.
Is there milli? What power of 10 do you see there?
Oh, no. So it's just 2.97 volts.
2.97 volts. Everybody show this to me on your calculators right now. I'm going to put the thing on pause. Okay, the next row, we would be multiplying 24.74 milliamps times 270. So clear the calculator and key in 24.74 EXP for the exponent. Change sign key to create negative and then enter 3. Does my display now show me 24.74 milli?
Yeah.
I'm going to multiply this by 270. Enter. I don't have to hit engineering because this is 00 on the end. How do I round this particular one, Sarah?
You just write it out, 6.68.
6.68 volts. Is everybody clear on how to round this value? Okay, 6.68 volts. Next one, clear. 24.74 EXP, -3 times 95. And this works out to be what value, Weiji?
2.35 volts.
2.35 volts. How many people agree? So far, so good? Okay. Now, a couple of things that we're going to double check before we continue. Some things that we want for you to remember are the following. Let me get this guy up here. And as we're looking at the share screen, the screen goes to show your summarization of the characteristics of, lost it there, sorry. Let me get this guy back on. Trying to connect. Okay. And let me make sure that we are on the share. So stop the share and let's go to share screen. I want this to share and hit share. Cool. Let me move this back over here so we can actually see it on our projector screen. Yay. All right, so on here, a couple of things regarding series circuits. Series circuits divide what?
Voltage.
Series circuits are what kind of dividers?
Voltage.
And what is the same in a series circuit?
Current.
Current. Formula number 4, V total is equal to what? VR1 plus VR2 plus VR3. So that is one of the double checks. The other double check is this. Take a look at item number 8. What's it say for number 8? It says the largest ohmic resistance will have the largest voltage. How about the converse of that? I asked you to write it down. I didn't put it on here, but I will in the future. The converse is, will the smallest ohmic resistance have the smallest voltage? Does that stand to reason? Okay, if we agree upon that, let's take a look at our circuit. So let me stop the share. Stop share. And come back to our circuit. Which one of these is the largest ohms? R2 is 270. Does it have the largest voltage drop? Yes, it does. Which one of these is the smallest ohms? R3, 95 ohms. Does it have the smallest voltage drop? Yes. So in other words, do I have proportional distribution? The answer is yes. The other thing is, do these guys add up to be 12 volts? Well, let's go ahead and punch this into the calculator. Clear. Let's go ahead and add these puppies up. 2.97 plus 6.68 plus, are you watching or doing? 2.35. Yeah, it's so interesting. You know, we're the generation of watchers. I want you to turn you into the generations of doers. When you go to that job interview, you're not going to sit there and watch the interviewer talk to you. You better be talking to the interviewer what you know. And if I hit engineering, does everything add up to be 12 in this case, or something really close to 12?
Yes.
Yeah. What happens if you end up with an 11.99? Are you going to be upset?
No.
Suppose you end up with a 12.01 or 12.02. Are you going to be upset? No. Why? Because we used rounded values. It's okay if you're 100th of a decimal place off. We used rounded values. In this case, it does work out to be 12 exactly. Isn't that nice? Cool. Now, when we go to do the measurement of these, when you go to do the measurement of these, the values that you're going to measure, so your VR1 is going to come out to be 2.97 volts right here. Your VR2 is going to be 6.68 volts over here, and your VR3 is going to be 2.35 volts over here. And I saved some space so that we can write these values down. So far, so good?
Yeah.
Now, the next step you're going to have to watch very carefully and listen very carefully. This is on Zoom. And as it is on Zoom, I will be able to get the Zoom recording of tonight's lecture. And then I will do some editing. Then I will transform it into an MP4, and then the MP4 I will then upload to my YouTube channel, and I will send you all the YouTube links so you can review these calculations and these processes over again, okay? So watch this very carefully. What I'm going to have you think about right now is this. How do we mark the polarities in our circuit? We mark our polarities, first of all, dictated by the polarity of the plates of the voltage source. Did everybody hear that? You start off by marking the polarity of your voltage source. Here's my voltage source. Short plate, long plate, short plate, long plate. Which plate is positive?
Long.
Because it's positive to be what? Long, and negative to be short. So this side is positive. Mark it clearly with a big plus, and this side is negative. So far, so good? Okay. Now the electrons have what polarity?
Negative.
Negative. The electrons leave what side of my source?
Negative.
Is that the top or the bottom?
Bottom.
The bottom. So watch this very carefully. Pay attention to this arrow coming down. That's my electrons flowing from the source. Did you see this? Did you mark this on your drawing? Not later, now. When it hits this corner, it's going to go to the right. So here's the electrons moving in this direction to this corner. Once it hits this corner, it's going to go up. Once it hits the corner of D, it's going to go to the left. Here, 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 here. Once it gets to A, it's going to go down to the positive plate. Do I have the direction of electrons flowing in this particular circuit drawn? Now, looking at the face of the clock. Okay, we have another 20 minutes. It's almost done. Look at the face of the clock. The second hand moves in a clockwise direction. Everybody see the second hand on our clock on the wall?
Yep.
Okay, now take a look at the circuit that I have on paper. In which direction is electron current flowing? Is this called clockwise or counterclockwise? Uh-huh. So electron current equals CCW. What does CCW stand for? Counterclockwise, okay? Sometimes it goes that way, sometimes it goes this way. Because of how I drew the plates and this schematic, we call it counterclockwise. Everybody okay with the direction? Yes, Isaac?
How do you find out which way the current's flowing?
Well, as I said, the electrons flow from, because they're negative, they flow from what plate of the source? It flows from the negative plate. So if it flows away from the negative plate, in this case, it's flowing down. Once it flows down to this corner F, where is it going to go? It's going to go to the right. And the electrons will continue until it hits E. Once it hits E, where's it going to go? It's not going to go to ground. This is simply a reference point. No electricity goes to ground. It will then flow up to D. And once it hits D, it's got nowhere to go except to go left. Once it goes through all of this, it hits A. It's got no place else to go at A other than to go down to the positive.
But why does it come out negative?
Why does it come out of the negative? Because the negative plate of the source is the source of electrons. Okay, the negative plate of the voltage source is your source of electrons. We talked about that on day one, and yeah, you missed day one, right? It's okay. Just keep asking those questions, Isaac. If they come up, I don't want you to miss anything. I appreciate those questions, and your classmates do too. Not everybody caught that. So they leave the negative plate. Now, a couple of things here that you need to make note of, and this is in your lecture notes. Electron current, in this case, happens to be counterclockwise, but here are some absolutes. Electron current, number one, always flows from negative plate of your VS voltage source, comma, through the circuit, comma, to the positive plate of VS. So I've done some abbreviations there, but read that through with me. It says electron current always flows from the negative plate of the voltage source, comma, then what? Through the circuit, comma, to the positive plate of the voltage source. Okay? We need it phrased that way in order to be accurate. And if we read this definition and we see how the arrows are drawn, does the electron current actually flow from the negative plate? It has to flow through the circuit. And does it end up at the positive plate of the source?
Yes.
Done. That's definition number one. Definition number two, equally important. Electron current always flows from negative side, I'm going to abbreviate negative, just NEG, negative side of a device, comma, through it.
We can't see the bottom.
Oh, so sorry. Thank you. I will adjust my camera so that now you can see all of it. Yay. This way. Make it a little straighter. There we go. All right. Negative side of a device through it, comma, to the positive side of that device. Very important observation, very important point to make note of in your journals. So these two components of electron current. Electron current, definition number 2, always flows from what side of the device? From the negative side of the device, then what? Through it to where? To the positive side of that device. Now, with that phrasing in mind, take a look at how the electrons are flowing through R3. Look at R3 very carefully. R3, does it have electrons flowing in the right-hand lead of R3, going through it, and leaving the left-hand side of R3, yeah?
Yeah.
So how are you going to polarize each side of R3? What would be the side where the electrons are entering the device, according to definition number 2? This would be what polarity?
Negative.
It would be, how many people agree with negative? Read your definition. Electrons always flow from the negative side of a device through it to the positive side. This must be, the entry side must be negative, the exit side must be positive. The electrons always flow from the negative side of the device through it to the positive side of that device. Is R3 polarized? The left side should be positive, the right side, excuse me, the right side should be negative, the left side should be positive. I think I spoke that correctly a moment ago. All right, how do we polarize R2? What polarity? Well, look at how the electrons flow through it. It flows in the right side, through it, out the left side. So the right side should be what polarity, my friends?
Negative.
Should be negative. And the left side should be positive. Very good. R1, the right side should be what polarity?
Negative.
Because this is where the electrons are entering. The electrons are flowing through it and exits the left-hand side. So this side must be positive. Very good. So now do we have polarities marked across the resistors? Very good. Very, very good. We filled in the VIR chart. We have voltages written across the values of the resistors. Everything corresponds. Now I'm going to take a moment and talk about voltages at specific points with respect to ground. Here's part of the homework that you're going to be looking at. So on this same circuit, not only did we fill in the VIR chart, but you're also going to be looking at the following information. We would be looking for the voltage A. The voltage A, when you see a single letter, remember, voltage is always measured between how many points?
2.
2 points. There happens to be a red lead and there happens to be a black lead. Okay? Red lead and a black lead. There's no way to get around it. You're always measuring between 2 points. Now, when you see a question asking you for voltage at point A, well, that means you're going to put the red probe at that letter. The letter that's specified. Where are you going to place the black probe? The black probe will go to, my friends, ground. Do I have ground specified here on my paper? Once this display unfreezes, uh-oh, I'm about to lose it. Yeah, I'm about to lose this image. Hold on one moment. Let me put this on pause. There we go. Thank you. All right, so my red probe is at point A, my black probe is at point ground. And there's a couple ways to read this value. One way is to read it straight down and then over to the black probe. And the other way is to read it from here across the top and straight down. Well, watch. If I'm at point A and I want to read the short path to ground, the very first polarity the red probe sees as I come down is what polarity? Positive. Positive what value? 12 volts. And I'm now over here. So VA is equal to plus 12V. And once I'm here at point F, I still have to venture towards ground. Well, guess what? Point F and ground are the same point. It's one wire. So there's nothing else to add. So what is my voltage from A to ground? It is a positive 12V. Is everybody okay with VA? Now, suppose I go the other way, because I said it should be valid if we go the other way. If I go the other way, my red probe being pulled towards the black probe, the very first thing we encounter is what polarity? Okay, so I have a positive. What value do I encounter? 2.97V. And I'm going to add that to. Now I'm at point B. At point B, do I see two polarities? I see a negative and a positive, right? Which polarity do I take is the polarity as I'm pulling towards the black probe. So that polarity must be what? Now, right here, I'm pulling towards the black probe. So I'm pulling in this direction. It will be a positive, what value of voltage? So positive 6.68 volts. And I'm now going to add that to, now I'm at point C. At point C, and again, I'm pulling the red probe towards the black probe. What polarity do I encounter right here? Positive, how much? 2.35, so 2.35 volts. And guess what? We already did that earlier. That adds up to plus 12 volts, yes? So do I have a definitive value for VA with respect to ground? And I read it this way. This is read as voltage at point A, and this is a phrase we often use, with respect to ground. GND is my abbreviation for ground. Everybody okay with that? With respect to ground. The last one I'm going to do for you is this. I'm going to do something pretty obtuse. I'm going to do DB. Voltage between two very specific points, D and B. If I show you two letters, the first letter gets what color probe? The red one. The second letter gets what color probe? The black one. So when you're given 2 points, the first letter will be the red probe, the second letter will be, so watch what happens. I'm going to put the red probe on D. Boom, there it goes. It's physically on D. And the second probe is on point B, so I'm physically going to put that at point B. Now, my job, in order to write down the value, is to count the voltages between D going to B. When we go to do this, what does the red probe see in terms of polarity as we pull from the red probe towards the black probe? What's the very first polarity it sees? Negative what value? So we encounter a negative 2.35 V. We're going to add that to, now we've gone through the resistor. Now I'm at point C. I've got one more resistor to go. What polarity do we see here? Negative. What value? Negative 6.68 volts. Add that together. What do you have? So clear. Turn it on. First go. 2.35 plus negative 6.68. We end up with? No. We end up with? Negative. Yeah, don't just call out the value. Should be negative 9.03 volts. How do we know that's right? Let's go the other way around. Okay, we went the short way around from here to here. Well, D to B can also be counted the long way around. So watch this if I go the long way around. Here's D. Anything between D and E, my friends? Nothing. Anything between E to F? Nothing in here, yes? So now I'm almost there. Watch this. VDB, if I go the other way around, what do I encounter now going up to point B? I encounter a what? A negative 12 volts. I am now at point A. I've got one more resistor to go between A and B. What polarity does it see first? Positive. So I'm going to add that to a positive. What value of voltage? 2.97 volts. What is a negative 12? So here is a negative, change sign 12. Add a 2.97. Bingo. What does the display of the calculator show us? negative 9.03 volts. This, my friends, is how you reconcile voltages at single points with respect to ground and voltages between two specified points. First point always gets the red probe, second point always gets the black probe. Okay, so that's plenty for now until we meet again on Thursday. Everybody okay so far? All right, I really appreciate you guys hanging in for a few extra minutes here, and I look forward to seeing you all on Thursday.